Hello, everyone. Thank you for joining us online today. My name is Meg Olson, and I'm the Executive Director of the Canadian Water Resources Association. Joining us today is Jung-Ho Kim with McMaster University and Kautemuk Sahagun with the University of Calgary for the first presentation in our webinar series with the National Hydrologic Service on the research conducted through the Flood Hazard Identification and Mapping Program. The Canadian Water Resources Association is a national organization dedicated to advancing the sustainable management of water resources across Canada. Our members include professionals, researchers, biologists, conservationists, and policymakers working together to address critical water challenges. CWRA hosts a variety of events, including webinars, workshops, and our annual national conference, which will be held in Penticton, BC this year. If you like this webinar series, be sure to check out our other events and our other webinar series online on our website. We will be posting a link in the chat to our events page, as well as some other links today that you can follow up on. This webinar is part of the 2025 CWRA webinar series in collaboration with Environment and Climate Change Canada's National Hydrological Service, NHS. As part of this exciting series, we are highlighting groundbreaking hydrology and hydraulics research conducted through the Flood Hazard Identification and Mapping Program and showcasing the latest advances in flood mapping science across Canada. This series is designed for flood mapping practitioners, researchers, interested parties, and the general public, offering a unique opportunity to hear from subject matter experts at no cost. These webinars and some accompanying materials will be available in both English and French, with recordings and additional resources accessible online after these sessions. Before we begin, I would like to acknowledge the land that I work on. If you like, you can also include your own land acknowledgement in the chat window at this time. I live in Toronto, in the watershed of Lake Ontario, which is the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabeg, the Chippewa, the Haudenosaunee, and the Wendat peoples. It is now also home to Inuit and Métis peoples, as well as other Indigenous peoples from across the world. I know that we are all coming from many different traditional territories and many different watersheds today. CWA has created an Indigenous Relations Committee to support the organization in its work towards reconciliation and allyship with Indigenous people in sustainable and effective water management in Canada. This is important to us, and we are committing funding and volunteer and staff time to this work. We welcome feedback and advice on this journey. Before we dive into today's presentations, I'm pleased to welcome Emmanuel Sims from Environment and Climate Change Canada. Emmanuel will provide a brief introduction to the Flood Hazard Identification and Mapping Program.
Thanks, Meg. Hi, I'm Emmanuel Sims, Water Resources Engineer with the National Hydrological Service in Ottawa. The next webinar in this series will take place on February 25th, featuring presentations from Mélanie Trudel and Martin Clark on advancing flood mapping and land modeling in Canada. For more details on upcoming events, please visit the CWRA website. You can move to the next slide. Here's the links. Yeah. So here's a quick overview of the Flood Hazard Identification and Mapping Program, known as FIMP. The FIMP launched in 2021-2022, and the continuation of the program launched in 2023-2024, with the current program ending in 2027-2028. Natural Resources Canada leads the FIMP in close collaboration with Environment and Climate Change Canada and Public Safety Canada. FIMP funds flood mapping projects in close collaboration with provincial and territorial partners. The cost sharing program is 50-50 with provinces and 75-25 share with territories. In the breakdown of the program funding above, the flood mapping projects with provinces and territories are included in NRCan's funding. The goal of the FIMP was to contribute funds to research. Environment Canada funds research streams dedicated to incorporating climate change into flood maps. This webinar series focuses on the outcomes of the research funded by Environment Canada completed during the first phase of FIMP. NRCan funds research streams related to regional flood modeling and inclusion of Indigenous traditional knowledge into flood mapping projects. We look forward to sharing the outcomes of the research with the larger community. And with that, I will pass it back to our host, Meg.
Thanks, Emmanuel. It looks like we have a lot of people joining us online. Wonderful. I just have a few more notes about some housekeeping today, and then we'll start the presentation. If you would like to listen to this presentation in another language, please click on the globe icon on your panel and select your preferred language. We are recording this webinar in both French and English, and the recording will be freely available on our website in the next few weeks. Questions will be answered after each presentation and then again after the panel discussion that will follow. If you have any questions or comments at any time, please type them into the question tab on your control panel. When we discuss the questions, I may combine related questions or paraphrase the question to make it easier to read out. If I misrepresent the question you asked, please follow up by sending a note through the same question area, and we'll make sure to get it clarified. During the talk, we'll be posting some links as well, in case you want to save those to follow up, so check your dashboard heading for those. Through the Zoom interface, you also have the option to turn on captioning for today's event, if that would be useful to you. Captions are available in both French and English. Now, to introduce our first speaker, Dr. Jung-Ho Gum is a research associate at McMaster University, holding a PhD in water resources engineering from Utah State University. His research focuses on hydrology, water resource systems, and engineering, as well as the development of decision support tools for water resource and quality management. Dr. Gum has contributed to various projects involving hydrologic modeling, flood forecasting, and early warning systems, and the design of hydrometric networks. All right. And Dr. Gum, all yours now.
Okay, so I hope all of you can see my screen. Okay.
Yes, looks clear.
Okay. Okay. Hello, everyone. Thank you for having me here and joining today's webinar. My name is Jung-Ho Kim, a research associate at McMaster University, and I am pleased to present hydrologic modeling in Ontario for flood hazard identification and mapping. And before we begin, I'd like to acknowledge my co-authors, Russell, PhD candidate, and Barshad, a former postdoc, and the PI and professor, Dr. Pauline Coulibaly. This project has been a collaborative effort bringing together expertise in hydrology, flood modeling, and computational science. And we are excited to share our findings with you today. Now let's go into today's presentation. This presentation is a part of outcomes from a FIM project. And the hydrologic modeling part of the program includes flood frequency analysis, model agnostic framework, which is designed to streamline hydrologic modeling without being tied to a specific model, and model-specific framework, where we integrate and test hydrologic models tailored to specific applications. I'll also highlight how these frameworks are applied across Ontario's hydrometric network using data from 85 stations, which is initially considered, but 49 stations selected in the end. Now let's go into the modeling frameworks used in this study. To ensure comprehensive hydrologic modeling, we employed the following processes: domain selection, model agnostic framework, model-specific framework, hydrologic model simulation, calibration, and validation. The model agnostic framework is designed to be flexible and applicable across different models. This approach allows us for a standardized workflow, making it easier to integrate multiple data sets, tools, and computing platforms. For this framework, we utilize several data sets, including RDRS, land cover, and soil classes. And to process these data sets, we have used GIS and Python-based tools, including GIS tool, data tool, and EasyMore. I'll explain these tools in the later slides. The next approach is the model-specific framework, where we applied well-established hydrology models. These include MASH and HYPE and SUMA. To route water through the river network, we have used Mizroute, which is a standalone routing tool that integrates with these three different hydrology models. And I'd like to acknowledge that these frameworks were developed through collaboration with the University of Saskatchewan and the University of Calgary. And all of these tools and frameworks were deployed on the Graham HPC cluster, a higher performance computing facility supported by the Digital Research Alliance of Canada. This computational power enabled us to run multiple large-scale simulations efficiently. Let's talk about how we selected hydrometric stations for this study. The first step was defining the domain, essentially identifying the regions and watersheds that would be included in our analysis. For this purpose, we relied on Merit Hydro, which is a global hydrography dataset that provides high-resolution river networks and catchment delineations. Initially, we identified 85 potential hydrometric stations across Ontario. These stations were chosen based on the availability of annual flow and peak flow data, which are critical for flood frequency analysis and model calibration. However, not all stations were suitable for our modeling approach. To refine the selection, we applied a set of criteria to evaluate station reliability and hydrologic representativeness. And the key considerations include catchment integrity and alignment with river networks and headwater classifications, and also upstream influence. After applying these filters, we finalized 49 stations out of 85 stations that provided the most reliable and representative hydrologic data for model validation. So next, I'll go into more detail on the selection process and the final distribution of these selected stations. In refining our selection of hydrometric stations, one key reason for exclusion was when the outlet of the Merit Hydro catchment was in the middle of the water body. This happens when a station is located within a lake, reservoir, or large wetland, rather than at a natural river outlet. In such cases, the station does not accurately represent the total upstream range area. So including these stations could lead to discrepancies between observed and simulated flows because hydrologic models typically treat catchment outlets as discharge point, not the intermediate locations within a water body. So this would introduce errors when calibrating and validating the model. Another key reason for omitting certain hydrometric stations was their location in the middle of a Merit Hydro rich segment rather than at a natural catchment outlet. As you can see, the station locations in the middle of the ridge segment. In hydrogen modeling, river ridges are typically defined as continuous flow segments between major confluences or outlets, like here or there. A station placed in the middle of a ridge does not capture the full contributing drainage area, leading to incomplete flow measurement. A third reason for excluding certain hydrometric stations was when they were located in the upper part of a Merit Hydro rich segment, and also the catchment was headwater. Similar to the second reason, stations located in the upper part of the rich segment in the headwater catchment, the station cannot represent any of catchment. So these kind of stations were excluded. But in some cases, we encountered stations located in the upper part of a merit hydro-rich segments. For example, located here of this rich segment, but it's not located in the headwaters. And in this case, instead of outright removing these stations, we assign them an up flag for further evaluation. Once a station is assigned an up flag, its flow is represented by the sum of the upstream catchment flows rather than being treated as an independent outlet. So the flow at this location is sum of these two upstream river reaches. So those stations were included in the analysis. Now that we have finalized our selection of 49 hydrometric stations, these stations cover a total of 721 catchments spanning key watersheds, including the Great Lakes Basin, the Ottawa River Basin, and the St. Lawrence River Basin, etc. Even though the catchment couldn't cover the entirety of Ontario, this distribution ensures that our hydrogen models capture diverse hydroclimatic conditions from urbanized watersheds to forested and agricultural regions. In addition to their geographic spread, these stations were chosen to support multiple hydrologic models, as I said, MESH, HYPE, and SUMA. To drive these hydrogen models, we utilize RDRS version 2.1 as the primary meteorological forcing dataset, ensuring consistency across all simulations. By selecting stations across different hydrologic regions and integrating them into multiple modeling frameworks, we established a robust foundation for flood hazard assessment in Ontario. Now, let's shift our focus to the model agnostic framework, which is a key component of our approach that enhances the flexibility and efficiency of hydrogen modeling. The purpose of this framework is to streamline data processing and enhance interoperability between different hydrogen models. Instead of being tied to a specific model, the model agnostic framework provides a standardized workflow that allows various models to be implemented efficiently. So to ensure consistency across different models, we incorporated several critical data sets, include, as I said, RDRS, which is a high-resolution reanalysis data set providing meteorological forcing data set from 1980 to 2018. And the key variables include precipitation and air temperature, specific humidity, surface pressure, wind speed, downward solar radiation flux, and surface incoming infrared flux. And land cover data is used to identify dominant land use types, which influence surface runoff, infiltration, and evapotranspiration. And also soil classes, which is essential for determining soil infiltration capacity and subsurface flow characteristics. Now let's take a closer look at GIS tool, one of the key tools used in our model agnostic framework. GIS tool is a GIS-based tool designed to efficiently process geospatial datasets for hydrologic modeling. It plays a critical role in preparing the necessary inputs for hydrologic simulations by extracting and analyzing spatial data related to land cover, soil properties, and topography. The key functions of GIS tool include efficient zonal statistics calculation, soil texture classification, and elevation analysis, and geospatial data cropping and processing. And this tool is available through this GitHub address. Next tool, data tool, is a hydrologic data processing tool specifically designed to handle large-scale meteorological forcing data sets for use in hydrologic models. It plays a crucial role in extracting, cropping, and formatting input data from high-resolution climate data sets. So it processes RDRS, meteorological data, and geographic cropping and subbasin mapping, and also it can do temporal data processing. And the third one, EasyMore. EasyMore is a hydrologic remapping tool that plays a critical role in redistributing meteorological forcing data to match the spatial configuration of hydrologic models. And once we extract and crop climate data using data tool, EasyMore ensures that the data is accurately mapped to each subbasin in the model domain. All the tools we've discussed, including GIS tool, data tool, and EasyMore, developed by the collaboration with University of Saskatchewan and University of Calgary, they were deployed on the GRAM HPC cluster. And also, here, Merit Hydro provides provided the high-resolution topographic and hydraulic data, which is crucial for defining watershed boundaries, river channels, and flow accumulation paths. We extracted the geofabric and river network from the Merit Basin database, which is a global vector hydrography database derived from 90-meter Merit hydro data. So let's briefly talk about the models, the hydrogen models. First one is MESH, one of the key hydrogen models we've used in this study. MESH, the MESH model is developed by Environment and Climate Change Canada. The big advantage of MESH is that it's highly flexible and works at different scales. Whether you're modeling a small watershed or a large river basin, MESH can handle it. It also lets us test different model components under the same experimental setup, making it greater for comparing results. MESH has actually evolved from WATClass, a model developed at the University of Waterloo, which combined the Canadian land surface scheme with WAT flood. Over time, it's been refined through collaboration with the University of Saskatchewan and the University of Calgary. And the second model, HYPE stands for Hydrological Predictions for the Environment. And it's a semi-distributed process-based model developed by the Swedish Meteorological and Hydrological Institute, SMHI. It's widely used for stream flow forecasting, utilized for flood and drought predictions, and also climate impact studies, because it can evaluate the effects of climate change on hydrological processes. It has been implemented in many regions, including Sweden, Europe, Africa, Asia, and globally. And worldwide, for example, the worldwide HYPE model, it can offer hydrological insights at global scale. The third hydrologic model is SUMA. As the SUMA stands for Structure for Unifying Multiple Modeling Alternatives. It's a flexible and modular hydrologic modeling framework developed by the National Center for Atmospheric Research. SUMA allows us to customize and compare different hydrologic processes within a unified structure. This makes it extremely useful for testing different modeling approaches and improving our understanding of hydrologic variability. Now that we've covered 3 hydrologic models, MESH, HYPE, and SUMA, and let's take a look at how they perform before calibration. This slide presents interannual hydrographs, showing how the model simulate stream flow over multiple years for a specific hydrometric station. For this case, Grand River at Gard 02GA003. Um, at this stage, of while we are doing the project, these are non-calibrated results, meaning the models were run using default or general parameter values without calibration yet to match the observed data. This gives us the first look at how well the models are representing streamflow dynamics before making any parameter adjustments. So what do the results tell us? So first, the overall streamflow patterns. We can see how each model represents the seasonal flow variations, including peak flows in wet seasons and lower flows in dry seasons. And also differences between models, since MeSH, HYPE, and SUMA use different process representations, their initial results may show variation in peak timing, magnitude, and base flow conditions. And also, of course, this result tells us that the need for calibration. The model needs parameter adjustment to improve its own accuracy. For this slide, it's also non-calibrated model results, but for another key hydrometric station, Humber River at Weston 02HC009. The Humber River at Weston is located in a very highly urbanized watershed, meaning that impervious surfaces, stormwater management infrastructure, and urban runoff patterns significantly impact stream flow. Similar to the previous slides, this figure presents interannual hydrographs comparing how the three hydrology models simulate stream flow over multiple years. Since these are non-calibrated results, we are looking at how the models perform using their default settings without any calibration to match the observed data. We expect this watershed to have flashier runoff patterns, meaning sharp peaks after rainfall and rapid declines in flow. Some models might capture this better than others, since each model has a different approach to handle runoff, infiltration, and base flow, and other hydrological processes. Their predictions may vary in terms of peak magnitude and recession rates. The third example is Bonsha River at Renfrew. It represents different hydrologic settings compared to the previous two stations. Unlike the highly urbanized Humber River, this watershed is less influenced by impervious surfaces and has more natural flow conditions, making it an interesting contrast in how models behave. Again, we are looking at interannual hydrographs, which compare the three models, streamflow simulation before calibration. With these non-calibrated results in mind, we move on to the calibration and validation phase, where we refine these models to ensure they align more closely with observed streamflow data. Now that we've reviewed the non-calibrated model results, let's summarize what we've learned and discuss the next steps for improving these hydrologic simulations. So far, we've built a model agnostic framework that streamlines hydrological modeling by using standardized data sets like RDRS version 2 and land cover and soil data. This approach made it much easier to run multiple models side by side and compare their performance. We tested here MeSH, HYPE, and SUMA on Ontario's watersheds, each bringing different strengths and challenges. And the non-calibrated results showed us that while all three models captured general seasonal patterns, they varied in their ability to simulate peak flows, base flow conditions, and overall stream flow dynamics. However, we cannot assure the values as they are not calibrated yet. So because of that, the immediate next step is calibration and validation to ensure robust and reliable performance. Right now, they are running on different settings, so adjusting key parameters will help align simulations with the actual observations. The ultimate goal is to develop reliable tools for floodplain and hazard mapping, making sure that our models are not just scientifically robust, but also practical for decision making. With these improvements, we can help communities prepare for extreme weather and manage water resources more effectively. Thank you for listening to my presentation.
Thank you very much, Dr. Gum. We do have a few questions, but before I ask those, I wanted to remind you all that if you do have any questions for Dr. Gum, please type them into the questions tab now. We're also going to be having a panel discussion after Dr. Vidrio Sahagun's presentation, so that will be another opportunity to ask questions as well. There were a couple of questions on some of the time series, some of the data that you showed. The first question is, in the comparison between the three uncalibrated models, what is the difference between the three observed time series?
Um, I do not understand what means the three observed time series, but um, actually except the motor configurations, all the input forcings and like all the input forcings are the same for the three models. So time periods, like time periods are the same for the models. And yeah, so when like for this applications, there was no like the calibration has not been done yet. So for the calibration phase, like immediate next step, yeah, we will collect the observed time series for the 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 time period that we have applied, which is the same with the RDRS or availability from 1980 to 2018 and collect the data and calibrate, use it for calibration.
Okay, thank you for clarifying. Another clarification question was, in the streamflow presented, was an observed streamflow part of the plots, or were those only modeled streamflows?
It's only modeled. Yeah.
Only modeled.
Yeah.
Okay. Um, Another question, was any data used from the provincial government to help derive model and routing parameters?
What's the question again?
Was any data used from the Ontario provincial government to help derive any of the model and routing parameters?
Don't think so. Like the data set I have used as I presented, the for the input forcing RDRS and soil data and Vancouver data is not provincial but global. So like Canada wide. So yeah, it's not only for Ontario but can be applied to any Canadian provinces and territories.
Okay, thank you.
Mhm.
And then another question, provided that people are working on regional flood mapping, can these hydrological models, MESH, SUMA, and HYPE, contribute to the mapping applications?
Oh yeah, I think so. Yeah, that's our like goal. So like develop the easiest way to apply these models in floodplain mapping.
Okay.
Yeah.
What is the ultimate goal of this study? Is it part of a flood modeling to create hazard mapping?
Yes. Yeah.
All right. And I'm going to take the next two questions and then we're going to move on to the next presentation. Um, so the meteorological forcing seems to come from reanalysis data. Um, is that data used instead of observed data? Um, and have you considered other hydrologic models as there are well-established models such as SWOT?
Like we decided to use like mesh hypensuma as an example, but for any like practitioners can choose their own models. But for this project, we only consider these three models, and yeah, so it doesn't mean that it's there's a restriction of using only these three models and we cannot use other models, but we can do. But these are just three examples of hydrogen models that we have used. And for the reanalysis data, actually, the purpose of reanalysis data is to provide better like spatial, like distributed, gridded data set. So like we have used it because like reanalysis data already like the observed station data is already embedded in the reanalysis data. So I think for the distributed forcing is the reanalysis data better present the input forcing.
Thank you. And for the last question for this segment, could you briefly explain about the conceptualizations you mentioned in the SUMA framework? And could you provide some recommendations to use this framework in cases of data scarcity?
Um, Actually, it's very not an easy question. So it's about hydrogen model, but so I would recommend go and read the documents about SUMA model for this question because it's
Okay.
about just the model. Yeah.
Okay. Thank you very much. I appreciate all of that. And thank you all for asking such good questions.
Thank you.
Um, And Dr. Gyum will be back when we do a bit of a panel discussion after this. But for now, our second speaker is up. Dr. Vidrio Sahagun earned a BSc, Bachelor's of Science in Civil Engineering from the University of Guadalajara, and a PhD in Civil Engineering from the University of Calgary. He is currently a postdoctoral associate in the Department of Civil Engineering at the University of Calgary. His research focuses on extreme hydrologic and climatic events under climate change and other human-induced changes. Thank you for presenting with us today, and you can get started now.
Thank you so much for that introduction, Meg. Really appreciate the invitation as well to share with you some of our work. Could you please just confirm you can see the presentation?
Yes, we can.
Thank you. So, hello everyone. I'm really happy to be here with you today and talk about this work on modeling water extremes in a changing world through statistical approaches. My name is Cuauhtemoc. I'm a postdoctoral associate at the Department of Civil Engineering at the University of Calgary. And first, I'd like to start with some background on the work we have done. And we have paid attention on water extremes because they have great socioeconomic and environmental impacts, and they have been intensified because of human activities. So you can look at this typical hydrograph, right? Where you can see the evolution of stream flow over time, and you will notice there are two very important extreme event cases, right? The first one would be like droughts. When we have too little water, we don't have enough water, and that's a big problem, right? And we face that problem in Alberta very recently. The other extreme is when we have too much water, right? Like flood issues. And again, in Calgary was not an exception. We had this very large flood in 2013, and there are floods all around Canada and around the globe. So we are trying to basically try to anticipate to both kind of weather extremes. But in this case, I will focus more on flood issues. And of course, the idea is that we don't only observe what already passed in the past, but also to predict them into the future. So we are mostly concerned how do weather extremes look like in the future. The problem is that they are extremes, right? So it's very difficult to predict them. And that's because of the Earth system complexity. So we predict extremes based on statistical approaches over the long horizon. We treat all the weather extremes as stochastic variables to quantify their variability and likelihood. You can just consider this illustration here at the bottom of the figure is the Lorentz typical scenario, where even very small changes in the initial conditions can lead to very complete evolutions of the phenomena, in this case, the weather extremes. For that reason, we often rely on statistics, and practitioners and decision makers usually assume that past statistics represent the future, ignoring the changes that may be caused because of climate change, water management changes, or land use changes as well. And it's therefore issue to answer questions such as, will droughts become more severe, prolonged, or intense in the coming decades? Or how will extreme rainfall change due to climate change? Or for example, what will the 1 in 100-year flood look like by 2050 or by the end of the century? Because of all this, we have been trying to develop next generation statistical approaches to predict water extremes with greater realism in a changing Earth. And in this presentation, I will cover two main topics, which is frequency analysis and also the post-processing of hydroclimate model projections. Of course, both of these components are very important for water security. So here's a quick reminder on statistical treatment for weather extremes and climate extremes, of course. We often start from some extreme event data, for example, stream flow data or rainfall data, and there should be extreme event data, and I'll elaborate in that in a second. From that data, we try to develop a statistical model. As you can see, in this case, the distribution is basically resembling very well the sample represented by the histogram. And we can use that model, that statistical model, to estimate some interesting stuff, such as the exceedance probability, which is represented by this red area. And now we can relate flood magnitudes to return periods, for example. We can use that model to analyze, model, and predict weather extremes now. And we can basically answer two main questions. For example, how often can we expect certain extreme event, some flood, or just the opposite? How large would a very extreme flood be in this specific case of study, right? And I like to highlight a couple of issues we face in practice. First one is the non-stationarity, because conventionally we assume the IID assumption, right? Independence and identically distributed observations. However, in some cases, we may notice that that doesn't hold because, for example, we can find trends. For example, in this scenario, the floods will be increasing or intensifying over the time. That implies that the probability distribution is in fact changing also over time. Therefore, if you have some infrastructure, say a dam, for example, with a fixed capacity, then the exceedance probability is also changing over time, and the return period is going down, meaning that we can expect more frequent and more frequent floods for that specific infrastructure. And the other issue is the uncertainty. We do not have perfect knowledge. So maybe rather than saying like a unique estimate, say what's the flood magnitude related to 100 years as return period, maybe we can just acknowledge our uncertainty and quantify it. So yes, we can say the point estimate, the most likely value, but acknowledging it will be at a given confidence level in a certain range. Now I would like to present a couple of contributions we have made in both issues. So first I will start with the uncertainty. In terms of uncertainty quantification, the profile likelihood method is a superior method for estimating uncertainty, but is computationally demanding and numerically unstable, especially under non-stationarity, again, like climate change, land use changes, or changes in water management. Therefore, we developed enhanced versions of this method for practical applicability. These are the RFPL method, regular falsy profile likelihood, and the RFGPL method, the regular falsy generalized profile likelihood method. In a nutshell, basically, the RFPL method focus on estimating the confidence interval bounds rather than computing the full profile likelihood. On the other hand, the RFGPL method used geophysical prior distribution to constrain the shape parameter to a realistic range. Basically, we can leverage our knowledge on the region, understand how floods behave in the region, and use that knowledge to constrain the estimates of the shape parameter of the extreme event distribution. In a nutshell, again, the RFPL method has the same accuracy as the original method, but with way lower computational demand in the order from 1 to 5% of the original computational demand. So it's more computationally efficient. By the way, I know these views are too small, but I had to use them this size because of the array. So if you have any questions, I will be more than happy to maybe zoom in and discuss in more detail. Regarding the RF-GPL method, on the other hand, we have higher numerical stability than the conventional method, and also we can constrain the uncertainty. We can reduce the uncertainty in the estimates. So these are two methods that offer notable advantages compared to what we already had out there. Now, going back to this general overview of probabilistic treatment of extremes, now I'd like to elaborate on non-stationary modeling and the contributions we have made in that regard. So in terms of non-stationary modeling, traditionally, we select the non-stationary models by ranking all the candidate models according to some performance metric, which could be pre-selected. Could be, for example, a theoretic information theoretic measure, such as the Akaki information criteria or some uncertainty metric. And we evaluate the performance of all the candidate models, and then we select the performance better or that ranks higher. However, this conventional approach has two problems. First is that it omits system understanding. So we are just basically just looking at the performance and select the best one. But we may have some knowledge actually, right, on the system, and we cannot account for that in this model determination approach. The other problem is the unreliable inference, because we have some property in statistical inference called ergodicity, and ergodicity doesn't hold under non-stationarity. So we don't really can make unreliable inference just based on a single time series. Therefore, we propose a model determination approach that leverages our knowledge of the non-stationarity based on the general decomposition of non-stationary stochastic processes. In the simplest form, you can just picture it this way. We have this non-stationary distribution, right? It's a distribution of the extremes, which is changing over time. And we can decompose it into two components. A stationary distribution, which represents the natural variability, and some non-stationary structure that describes the changes of the extremes over time. So this deterministic structure, for example, could be describing the climate change signal, the signal of change in land use or in water management. Of course, it can take more complex forms, but basically this is the idea behind our proposed approach. We tested it, and basically we found that this approach captures the underlying process better. It is more effective in selecting the right model, and also it avoids equifinality and uncertain selection of the traditional approach. Now, going back again, regarding to non-stationary contributions we have made, we know, right, that non-stationary predictions are hampered because we have limited extreme event data, and therefore that results in high uncertainty. In the conventional approaches, basically the data we use could be either annual maxima. In annual maxima, we take the full time series and we split it into years. As you can see, each year is here, and we just pick the highest event on record in each year. So you will see the red dots representing the actual data we'll use in extreme value modeling. The other approach is peaks over threshold. So we set a sufficiently high threshold, and all those exceedances, as long as they are independent, could be taken as the extreme event data. And we proceed with some conventional distributions, such as the ones that emerge from the extreme value theory, such as the generalized extreme value distribution, generalized logistic, the three-parameter log normal, the two-parameter log normal, Pearson, and of Pearson type 3 distributions. Now, there is another alternative we have been working on, which is leveraging ordinary event data. So we now can use the full data set and specifically take the ordinary independent events. For example, could be daily series if it's precipitation, or ordinary peaks if it's stream flow, and now use a different family of distributions, such as the metastatistical extreme value distribution, its simplified version, the beta binomial, or virtually any other ordinary event distribution. The advantage of that is that we can now leverage more data than conventional approaches do. So we develop non-stationary metastatistical approaches to leverage, again, ordinary events. The problem is, or the tricky part is, how can we model non-stationarity, right? So the first try in the metastatistical framework was proposed by Marani and Ignacolo, which basically use the set of annual distributions of the extremes. The set of annual distribution of extremes. So you can see that from one year to another, of course, there are some like chaotic variations, right? That's natural variability mostly. But in the first try, what we did was maybe consider that interannual variability was in fact because of changes in the system, say again, climate change. So that was the first try. Of course, you can see that the distribution of the extremes changes very randomly or chaotically, right? So it's not very useful for practice. So later on, there was a newer version proposed by Mara et al. In 2019, where they now introduced a non-stationary structure into the distribution. So now you can see we have more like organized variations in some parameters of the distribution, leading to more deterministic variation in the distribution of the extremes. So that was a very good advantage. But the problem is that these two existing approaches basically cannot explicitly deal with both non-stationarity, say climate change, and double stochasticity, the natural variability of the extremes themselves, but also the interannual variations because of natural variability. So we have double stochasticity in the system, and those distributions could not handle both at the same time. So we proposed a new distribution, the non-stationary metastatistical extreme value distribution, where we both account for the natural interannual variability in the parameters, and also we have this deterministic evolution of the extremes. So we can now again account for natural variability and climate change. We tested this proposed distribution and we have an improved performance because the proposed distribution performs better or similar than existing models, including conventional models and also metastatistical models. But at this point, you might wonder, like, if there are some distributions that perform similar to this new version, why would I care and use this more complex version, right? So we had the same question, and basically we found that the proposed non-stationary metastatistical distribution improves dealing with non-stationary stochastic covariates and helps for better predictions into the future. For example, let's say that we will describe changes in extreme precipitation as a function of a warming atmosphere, like increasing temperatures. Well, if you condition the distribution of precipitation on temperature, you will have these random variations, right? Because temperature itself is randomly changing, right? Now, if you account for that double stochasticity, you will have this beautiful, like continuously changing distribution of extreme rainfall, which now can be used for some extrapolation, which is not possible in the conventional approaches, simply because the covariate is stochastic itself. So that's the advantage of using the proposed non-stationary metastatistical extreme value distribution. So now let's get back to this original overview, right, of how we deal with water extremes. And probably the question you have in mind is related to this, right? We often want to see what do future water extremes look like, right? So we could model what happened in the past, but more importantly probably is what will happen in the future. How can we predict water extremes in the future based on historical data or some other tools? And I will say that arguably the mostly accepted approach for doing that task is using hydroclimate projections driven by process-based models. Basically, the typical modeling chain consists of assuming some shared socioeconomic pathway describing how humans behave or will behave in the future, and then use that scenario and go to a global climate model, which will be forced with those like emission scenarios, and it will solve some processes at a coarse scale. You use those outputs into a regional climate model that's called dynamic downscaling. And those outputs will require some post-processing, for example, using statistical downscaling or bias correction. And this is because both models contain systematic errors. So we need to remove those or increase their resolution. Then using that climate data applicable at the local scale, we can now feed a hydrological model and simulate what the future will look like in terms of, for example, stream flow. Again, that model probably will contain systematic errors, and we will need a last step of post-processing, for example, bias correction. Now, I would like to highlight one more contributions we did in terms of post-processing outputs from both climate models and hydrologic models. Using this modeling chain, we can now predict future extremes. Again, let me just introduce this couple of contributions we did in terms of post-processing hydrological and climate model outputs. We know that climate and hydrologic models produce systematic errors and should be corrected before using them in practice. However, existing correction approaches handle climate change poorly and struggle due to the limited data. Therefore, we developed novel correction approaches that model continuous climate change and leverage ordinary event data while focusing on the wider extremes. If you are not very familiar, the idea of correction basically is as follows. We do know the distribution of observations in the past, specifically, right? We have some observations. And when we simulate reality using a process-based model, most likely it will contain some systematic errors. So you can see that the model outputs in blue are different than the distribution in red. The idea of correction is just making the blue distribution match the observations distribution. So we need to do something in order for the blue line to match the red line. That's basically the idea behind correction, model bias correction. How we do that? Well, the most probably one of the most popular methods is quantile mapping, proposed by Panofsky and Breyer last century, where they completely ignored non-stationarity because that was probably not required at that time, right? So we can see that the distribution used to correct the model simulations was constant over time. However, in the red line, you can see that probably extremes are actually changing. This red line is a specific quantile, say the 20-year quantile. So the 20-year quantile is actually changing, but the distribution used to correct the model simulations is not changing. So we are missing some information there, right? To avoid this problem, later, several methods were proposed, such as trended quantile mapping, quantile delta mapping, and the CDF transformation proposed by Burger, Alex Cannon, and Michelangeli at the beginning of this century. However, as you can see, these methods basically assume an abrupt change, right? So we assume a stationary distribution in the baseline period, could be, for example, the historical period. And then as soon as we move to the future period or prediction period, the distribution used to correct the model simulations, it suddenly jump up, in this case, to reflect a relative change in the climatology or the hydrology. Again, we can see with the red line that actually that's not very realistic, right? I mean, it helps that simplification, definitely it helps, but it's not explicitly capturing that continuous change of the climate system and the hydrologic system. Therefore, we proposed in a recent paper, recently published in Water Resources Research, a non-stationary quantile mapping method where we explicitly, continuously capture the non-stationarity. Could be, for example, assuming a continuous and sustained change, or we can allow for the method to account for relative changes in the non-stationarity. So, for example, in the future, non-stationarity will intensify or weaken. We can allow that consideration in the modeling. We tested these proposed methods, and here, by the way, again, we leverage the metastatistical distribution, so we can use more data to avoid like extremely high uncertainty. We tested the proposed method, and we found that our approach is more realistic, is more accurate and reliable than conventional methods that I just mentioned, especially with typical long data sets. And the other thing is that the previous correction approaches have biased quantile matching. What does this mean? Well, basically, you may be bias correcting the 100-year quantile as if it was the 10,000-year quantile. So it could be competitive in smaller or shorter data sets, but similar to hydrological modeling, you will be getting probably close to right answers because of very wrong reasons. So that's an advantage. That's something we prevent in the non-stationary bias correction, explicit non-stationary bias correction. So this is a quick overview of what we have been doing in terms of research contributions, but we do have one more component in our work, which is the knowledge mobilization for the engineering practice. We do believe that any research that we conduct should be somehow benefiting actually the society, right? We need to translate or mobilize the knowledge for the societal benefit. So before doing that, we had a key question that you probably also may have had, and it's about understanding the engineering practices. And the question we had was, what is the state of practice in design flood estimation and how we deal with climate change? Unlike the US, for example, we do not have guidelines for practices in Canada yet. They do have the bulletin 17C, but we don't yet. So it's an open question, right? How do we actually estimate design floods in Canada? So we reviewed design flood estimation practices in Canada systematically based on many technical reports from the last 3 decades. And I'll show very quickly how this looked like, but by the way, this was published today, so you can now go to the journal paper and see the details. Basically, this is what we found in practice. In a summary, basically, we found that methodological variations are quite extensive. Non-stationarity is typically disregarded. So there are concerns and there are some commentary sections that say, okay, we are concerned about climate change impacts or land use changes impacts or some other impacts, but that's not explicitly captured in the design flood estimation practice. And the other thing is that uncertainty is often overlooked and estimation methods undisclosed. Of course, all these factors may impede repeatable workflows, reproducible results, and reliable design flood estimates. So, as I said, we need to improve engineering practice and consider climate change in design event estimation by mobilizing knowledge. So we developed a systematic framework for design flood estimation using flood frequency analysis with a workflow that facilitates repeatability, reproducibility, employing state-of-the-art methods that can account for non-stationarity, and releasing open source software to promote its wide implementation. Basically, this is how it looks like, the framework, and it helps you to answer very important questions such as, do we use a stationary or non-stationary approach? That depends on the case study, right? In order to answer that question, the framework has its own workflow for exploratory data analysis. And with this workflow, you can answer questions such as, are there significant trends? What kind of trends we have, like deterministic because of an external driver, or maybe just because of natural variability? Or maybe there are change points. Could be a sudden change, for example, because of water management and the construction of a dam, or maybe the beginning of a trend. All that is answered in that workflow. Then the model can make their decision, and the framework will help you to select the statistical model to use to estimate the parameters of such statistical model, quantify the uncertainty, and also quantify the model performance, and eventually lead to a systematic and coherent report that facilitate repeatability of the workflow. Of course, you don't have to do this like by hand. You can use this graphical user interface we developed, and I would like to describe it for you very quickly. This is a graphical user interface. It's very user-friendly. Basically, you can just import a CSV file and just select where you want the results at. In this case, it will create a folder in the desktop, and now you can run the exploratory data analysis to investigate the presence of signals of change, say non-stationarity signals. In this case, it found a change point, but we are analyzing the Bow River inbound, which is a RHBN basin, so it's free from human interface, most likely. And now you have the technical report, and you can see like if there are signals of change. In this case, we do have a downward trend. So floods in terms of magnitude are going down in Bow River at Banff. And now you can ignore that trend. use the business as usual approach, just ignore non-stationarity, and you will be able to select the best fit distribution using the software. In this case is the Pearson type 3, and you can see that graphically, but also numerically in this CSV file. You can change the metric as well. And anyway, in this case, it leads to the same distribution. So it seems to be a consistent decision. And now you can select the methods for parameter estimation, for example, L moments and the parametric bootstrap, and it will give you a new folder with all the results. So you will see graphically the frequency curve, the model performance of the distribution, also the estimates numerically, the point estimates and the confidence interval bounds, the metadata for workflow repeatability, and also the model performance assessment is there. And now you can actually account for the non-stationarity, say climate change in that case. So again, you can run the model selection. Here we leverage the first research contribution I mentioned in terms of model determination using the stochastic process decomposition. And you can see, again, the best fit distribution determined using the first contribution we made, and then run the parameter estimation and uncertainty quantification. Here you will notice that it's taking longer, right, compared to the stationary approach. Good news is that here we implemented the RFPL and RFGPL methods, which are more computationally efficient and numerically stable. So we are actually saving time. If you don't use the improved methods, you will take around from 20 to 100 times more of the time to obtain the estimates in this non-stationary context. And you can see now the frequency curve, how it's changing over time. So it reflects the observed downward trend in the annual maxima of floods. You can also look at the frequency curve at a specific time slice. And you can also, of course, see the numerical estimates, like numerically, confidence interval bounds and point estimates as well. And this software is already publicly available. So if you want to see more details, I would like to invite you to just scan this QR code. It will lead you to this paper. In that paper, you will find the link to the Zenodo page, which appears down here. So far, we have more than 700 downloads. So I believe it's been useful, and we expect to continuously upgrade this over the time. But now we have one more option for practice, incorporating research advancements. We applied that framework across Canada, and basically we applied it in several sites, and with some conditions, such as they have at least 40 years of data. We focus on populated areas with flood hazard maps. And yes, of course, we could identify there are non-stationary signatures, meaning we observe floods are changing in Canada. We estimated the flood yields, which is nothing but just the design flood divided by the drainage area, so we can more easily compare. And basically, you can find, for example, in these dots in black, how the color is changing over time. And changing color indicate a change in the magnitude of the design flood. Here, if you look at two specific sites, you will notice that if you ignore non-stationarity, say with the yellow line, you may be over-designing in some cases or under-designing in some other cases. So that's the consequence of ignoring non-stationarity. All this work has been published in several journal papers, and if you're more than welcome to look at them, and if you need access, just send me an email. I'd be happy to share it with you. So as a take-home message, weather extremes like heavy rainfall and floods may intensify with climate change, but their non-stationarity is often overlooked. We developed advanced methods for hydrological frequency analysis and bias correction that improve predictions and support adaptive engineering practices. We reviewed practices in floodplain mapping during the last 3 decades, and we found wide and undisclosed methodological variations in flood frequency analysis, all overlooking non-stationarity. However, we developed a systematic and software-supported framework for repeatable workflows for stationary and non-stationary flood frequency analysis. It is freely available and offers modeling flexibility while ensuring reproducibility of results. We applied the framework across Canada in the historical period and showed how ignoring non-stationarity might lead to over or under design and preparedness. And that said, I would like to say thank you for your attention. Of course, to acknowledge the support by Environment and Climate Change Canada, who funded this project. And here are some contact information in case you need access to any resource. And that will be it. Thank you.
Thank you very much for your presentation. We do have a few questions already, and so I will just get started with some of those. So the first one is this work based on an in situ or a regional frequency concept?
This is for, so far it has been developed. Okay, I guess you are talking about the framework, right? And if that's right, the framework is for a single time series. So that single time series most likely is at site frequency analysis, but if you perform regional frequency analysis, you can pull the data after some standardization, and it can also be used for that purpose. However, that investigation of regional homogeneity is not included yet in this package.
Okay. Since it is based on kind of a more of an in situ model, how did you manage the uncertainty that might have arisen from relying on observations at a single station?
So we do not do anything in particular with uncertainty. We just quantify it, right? So we offer the confidence interval bounds. Of course, that depends on the sample size you have. If you have a very long sample, most likely that confidence interval will be relatively narrow. If the sample is too short, it will be very wide. However, you can use the RFGPL method, for example, or the generalized maximum likelihood method for parameter estimation and uncertainty quantification, and you can leverage regional data in the form of a geophysical prior distribution. Again, that's not included yet in the framework, but can be done. We hope to incorporate that in the next version.
Okay, thank you. The next question is about statistical considerations in dealing with watersheds that have mixed regimes, so both rain-induced flooding and then snowmelt flooding. What do you have to look out for, and how do you deal with watersheds that are shifting from rain-induced due to climate change when there are very few rain floods in the historical record, but those are expected to increase in the future?
Yes, that's a great question. And the answer is that so far in the work I presented here, we do not account for that. So remember that the original assumption is independent and identically distributed. So one violation is non-stationarity, but you're completely right. The violation is like mixture of generating processes. That's another complexity we do have. That's a work we are performing right now. We are working, for example, with Paul Whitfield, and we are trying to address that as well. Again, the problem with that is that we will increase model complexity because we will now account for two different generating processes. Each could be changing in a different way. So you are accounting for both non-stationarity and multiple generating processes. So the model is too complex, and most likely, because of the data limitation we have, we will need metastatistical approaches in order to try to constrain the uncertainty level to an acceptable degree.
That's great to hear. Thank you. Um, And then the last question we're going to take on this particular presentation for now. There will be an opportunity to ask more questions afterwards. I think we're doing pretty well in time. Um, uh, and this person took from the presentation that the NSFFA approach is primarily based on identification of non-stationarity in the historical record. Is the method you presented able to take advantage of climate projections to identify potential new or enhanced non-stationarity effects into the future?
Sorry, if I understand, please let me know if I understand the question right. You are asking if I can use more data than just observations, but maybe using climate model projections?
It sounds like it, and if the questioner could follow up with any clarification, if that's not it. Mhm.
Okay, if that's the case, the framework itself, it just uses data. That's it. It doesn't really care if it's observations or climate models. However, climate models or hydraulic models, again, contain systematic errors. So what you can do is if you want to use those, is just make sure they have already undergone bias correction and use that data as the input data for the framework, and now you can conduct it.
Okay, thank you. That's really interesting, and it sounds very robust. Um, what we are going to do now is move into our panel discussion. So we have a series of questions that we're going to put to both Cuauhtemoc and Jung Ho, and hopefully they can speak about these questions for a little bit. We're going to do that for about 20 minutes. And then for the end of the presentation, we will have some more time, if anyone is still with us, to do some more question and answer for each of the presenters or for anything that has come up in the panel discussion. Um, so we can get started with that. Emmanuel, would you like to ask one of the first questions we have, or should I go ahead?
Sure, I can get started. So both of your presentations highlighted advanced modeling techniques. How can we bridge the gap between complex scientific models and practical applications for policymakers and local communities?
Go ahead, you go.
Oh yeah, actually, my presentation work with University of Saskatchewan and Calgary. Um, we introduced the model agnostic and model specific frameworks deployed in HPC clusters, and these frameworks enhance the usability of complex hydrogen models while maintaining flexibility in data processing and like comprehensive and consistent way of treating the data for the use for the hydrogen models. So like this kind of automating workflows, maybe practitioners can feel easier to apply different models without extensive technical expertise.
Yeah, and I will also say that I believe that knowledge mobilization is very important to enable practitioners to leverage any research advancement, right? Like to comment on two things. First, that I believe that sustained research to practice translation may necessitate two key changes. First, increased involvement of regulatory agencies and improved knowledge mobilization pipelines. We need standardized, coherent, and flexible workflows that require regulatory agencies intervention to review and approve, right? However, knowledge mobilization for the continuous evolution of practices will likely increase workloads for those regulatory agencies and require more investment to make them more robust to handle the growing demands. So I believe that that's one part, like the involvement of regulatory agencies. The other thing is how can we establish some pipelines to mobilize knowledge to the practice, right? Probably what we will need to have is some sort of like modular framework for applications, very similar to what just John was describing in his presentation, right? So he has this model agnostic framework where he can use basically any hydrological model, just plug in things or plug out, right? So in a similar fashion, I believe we can do in research to practice translation. If we have these modules, we can just update components of the workflow and streamline all the transition from whatever we do in research to practical benefits.
Yeah. I have a follow-up to that question. Have either of you had a chance to work with any practitioners or people kind of creating these maps in using some of the tools that you're creating yet? And what kind of feedback have you heard if you have had that chance?
Hey, this is the result from just first phase. So we couldn't do any communication with the practitioners yet. Maybe like like that can be realistic after the end of the whole film project. But
Great.
because this is the middle of the whole project, there's no chance to do that.
Yeah, in our case, basically, so we released the flood frequency analysis framework, and some people have downloaded it and tried to use it in their practice. So they have been sending us some emails, right, with some issues they have found with the software, or maybe they're not sure if their workflow is ideal, or maybe they look for feedback or something like that. So that has led to a interaction and communication with practitioners. And yes, we have identified ways to move forward with this project. And also we have implemented this framework in some courses here at the University of Calgary. So some students have learned them in the course, right? So they go outside to the practice world, and then they try to implement it and they identify some issues, and they go back to us and say, so here I found a problem that I will appreciate you address in the next update, right? So we have been kind of in the loop, but I agree with Jonko. This is like the first phase, and hopefully we can have some continuity and therefore improve it further.
It's really promising to see that's a part of the setup of the questions, like the idea that you can talk to people about what's going on in later phases and make sure that that's incorporated in the next steps. It's great to hear. And I will ask the next question. What strategies do you think can improve data sharing and collaboration across academic, governmental, and community stakeholders to enhance flood mapping?
Like, can I start, Carmack? Yeah, like for this kind of project is to like even though we are working on the film project, we cannot like for the research we cannot do for entire Canada. So, but like what as for as a like researchers in academia, like what we want to do is to um like show the most like promising or like state of the art way to like we are like we want to like develop some guidelines, for example. So using this, so like we if we publish our like outcomes deliverables after the project, like and then the government and community stakeholders can follow what we have discovered. So like after that, maybe standardized guidelines or data sets can help for the collaboration across academic, governmental, and community stakeholders, and also like developing a centralized data sharing platform, which is a repository where hydrometric and climate and land use data sets are openly available. Yeah, that's my thought.
Yeah. Yeah, and I have to acknowledge that I'm not the best person to advise on data sharing because most of our work is about methodological developments, right? So focus more on methods rather than data. But I would like to say that as someone that tries to develop methods, I do use data, and as a user, I have some perspectives, right? And as a user, I will say that there are probably three key barriers to accessing data. And probably one could be technical, another could be institutional, and the third could be, for example, social, right? And I'm not sure how to improve those, but I do believe that some very general ideas could include, for example, uh, standardized data frameworks, so we can sort of see some like uniform pattern of how data is accessible, right? So you don't have to learn like many ways to get the data. I mean, I do know that like netcdf files are very popular right now for especially for climate model data or something like that. But I do find like very different formats for the data. Also, open data platforms. Some of them are not very open or transparent, right? And also, of course, like capacity building and training, because I believe for some personnel, especially, for example, for early career professionals or grad students, for example, I believe it could be valuable for them to have some workshops where they learn how to access the resources and which ones are available for them, right? As an user, that's what I can say.
Thank you. Emmanuel, would you like to ask the next question?
Sure. So what advice would you give to practitioners looking to implement model outputs in real-world flood management projects, especially in data-scarce regions?
Um, like for like the answer to the to the second question, we are providing some guide how to map the floodplain. So, um, but if we focus on the data scarce areas, like I think there are like so many studies is currently like have done like outside this project. So I think we have to rely on those like specific. This is a like hydrologic modeling in data scarce region is another very big topic in water resources and hydrology. So we have to rely on that for data scarce regions. But for like outside that, like how to like advice to give to practitioners for this model outputs to real world management projects. Like I hope we can provide some guidelines how to map the floodplain.
I agree with that, and probably we can. One advice that could be useful is to keep in mind the project needs you have, right? So it's better to probably select a fit for purpose models. For example, maybe you don't really need something too complex for your specific project needs. So you can like balance like model complexity and data availability, just considering the hydrological context and again the project needs. Also, sometimes there are multiple data sources. So even though there might be a lack of observations per se, you can have, for example, reanalysis. That's better than nothing, of course, right? Or you can have some other data sources, interpolated data products, for example, in Alberta, that's also popular. Remote sensing data as well. So you can explore other data sources you have at your scope, right? And probably what I will say, and following up with previous Meg's question, is about uncertainty. The lack of data leads to a higher uncertainty in the estimates. So probably just quantify it and communicate how uncertain your estimates are is quite important. Otherwise, we just look at one specific value or some specific like flooded area or flood fringes or whatever, right? But we believe like it's a very exact estimate, and it is not. And it's because of the lack of data. So if we quantify and communicate that uncertainty, I believe it's more informative as well. And sometimes it's out of your control, right? You do the best you can do with the resources at your scope, and just be transparent with that is useful, I believe.
Thank you. We do have a few more minutes for this, so I think we're going to be able to ask the next few questions as well. So the next one we have is on including both climate change and land use changes in these models. So both climate change and land use changes influence the frequency and magnitude of flood events in Canada. Can you discuss a little bit how important it is for models and analyses, flood frequency analyses, to be able to explicitly take into account the impact of land use changes in addition to the impact of climate change when in the context of floodplain mapping?
Um,
And how much you see that addressed right now in terms of including both in modeling?
If I focus on the land use changes first, then like, yeah, flood risk is influenced by like urbanization, deforestation, or like agricultural expansion. Yeah, it affects runoff and infiltration rates. And if there is an updated land cover land use data sets, the model agnostic framework allows for like easier incorporation of it. So it's good. If there is no updated data set, although there is a significant change of land cover, the hydrogen models need to be recalibrated and revalidated with the observation after the change. And for for the climate change, it's a bit more like difficult question because like like in this application, we have used the historical data set, RDRS, but maybe like we can like forecast using climate data and then do the similar analysis, and then maybe we can find some differences between the current climate and the future climate. But the tool, the developed tool, like more model agnostic framework can help for like in both changes, I think.
Yeah, yeah, I agree with Jongo, and I do believe that accounting for land use is important with a varying degree of importance depending on the basin, right? So some basins are not that affected by land use, but some others are potentially very affected by land use. And land use change could be of several forms, right? Could be like urbanization, could be deforestation, could be agricultural expansion. And all those changes, of course, impact or can impact floods because it can alter the surface runoff, can alter like the infiltration, the water storage capacity, and all those have an impact on flood frequency analysis, for example. And how to account for that? Well, for example, in the statistical treatment for floods, you can use, for example, the percentage of impervious surface or accounting for the changes in land use characteristics as a covariate. So you can condition the changes in the floods depending on the evolution of that covariate, which could be how much of land has increasing its infiltration capacity or reducing that infiltration capacity. So in that way, you can, to some degree, capture how floods change because of changes in land use. But yeah, I believe that John Ho will be like the best person to highlight how to account for that in hydrological modeling, which is a different perspective, right?
Thank you. And we do have one last question. It's going to be slightly different from what's in our notes, but I'd like to know from both of you what you would like. You all are developing very, kind of advanced modeling projects. Uh, what is the most important, set of information you'd like your intended users to know about what you're developing and what you're trying to make sure that they have? Like what is the most important, information about your work that you want them to know? And then as a secondary question, just for, an average Canadian who is worried about flooding, doesn't quite know what's going on, is there anything that you would like, just kind of an average person, an average resident of Canada to know about your work?
Um, Simply, our work is to make our society safe, be safe. Yeah, like against flood. And so, and the practitioners, like what we are going to, um, yeah, it's simple and very hard question. Can you go first, Cormac?
Sure, sure. Yeah, I think that's an excellent question, and I will probably just phrase it as follows. I would say that floods is one kind of weather extreme, and weather extremes are too difficult to predict deterministically over the long term. So the best we can do is to just acknowledge it has some sort of randomness there, right? So we try to account for that using statistical approaches. So we can see how likely is an extreme event to take place in the future. But those extreme events are changing, right? Because of climate change, land use change, water management changes. So we are trying to do some research to predict the chances of those extreme floods into the future. And we are trying to move that research, to mobilize that research in order to be actually implemented. So when you find like in your government website, this flood map that says, okay, this is the area that is expected to flood on average once every 100 years. Well, we're trying to inform those modelers so their estimates reflect better what the future will be, right? And yeah, I will just say like it's important to acknowledge our system is changing and we need to invest resources to better prepare for the future so we can build more resilient communities to face what happens next in our lives in the future, I mean.
Okay.
Yeah. Did you have anything to add, Jungho?
Oh, no, no. Yeah, Cormac did all very well. So, yeah, no worries to add.
All right. Thank you very much. And thank you for all the additional insights you've added through those questions. I know that there's a second set of this work going on through the FIMP funding, and I think that there's additional things that are going to come out of that, but then there are also so many additional things to follow up on through what you've said today. We have about 25 more minutes scheduled for the event, and we do have a few more questions in the question and answer panel. So as long as everyone is comfortable, let's keep on taking questions until everyone has been able to ask what they'd like to ask today, if that's all right.
Yeah, totally.
Okay. And Samantha, can you help us identify who the next question is from?
Let's start with the question from Haida, and then a note for attendees during the Q&A period. If you'd like to ask your question live, please raise your hand, and I'll coordinate with Meg, and we can allow you to unmute, and you can ask the speakers your question live.
That's right. If you make it for the first hour and a half of the presentation, we'll let you talk. So the next question that we have then is, are these models and statistics applicable to very dry conditions where the soil water curve is most nonlinear?
Please correct me if I'm wrong, but this is my understanding. I believe that this question is about basically flood generating mechanisms, right? Because flood behave differently, not just because if they are driven by rainfall or snowmelt, but also, of course, the antecedent wetness conditions of the basin are also impacting the shape and magnitude of floods. So I believe we can consider that question as related to flood generating mechanisms, and what I presented today does not account for different flood types. But that's something that's part of the work is ongoing right now. So we're working on that, and hopefully we can incorporate that other complexity of the real world into our next generation prediction methods. That's a very good question. Thank you, Hida. Or Haida, sorry.
Thanks, Cuauhtemoc. I have a hand from Ara. Ara, if you'd like to unmute, you can ask your question next.
Do you hear me?
Yes, we can hear you.
So, hello everyone. Thank you, Django and Cuauhtemoc, for the presentations, and thank you, CWRA and Emmanuel and every others for organizing this. I think I wrote my question in the chat, but I just was wondering, Cuauhtemoc, in your study, you, if I remember correctly, studied both precipitation, rainfall, and flow. Since flow, well, generally, the runoff is more complicated than what is actually occurring in the atmosphere. Was wondering if you had you saw major performance differences when looking at rainfall versus flow for your for your new flood frequency analysis approach.
Sorry, just to confirm, so your question is about like how can we prepare to those extremes, like in terms of
No,
measures?
so I think you studied both precipitation, rainfall, and flow, right? So the frequency distribution of both these two events were studied, right? Is that right?
Yes.
So in my experience, you can have a certain amount of rainfall and occurring in different years. So basically the frequency analysis may be a little bit easier to do comparing to the flow dynamics, because sometimes there are reservoirs, delays in the flow, different types of procedures. So yeah, what I'm trying to ask is, did you notice any major performance difference of your models working on rainfall versus working on flow?
Yeah, okay, I got it now. Yeah, and I would say that in general, in terms of, let's say, the statistical perspective, it's not that different, because if we are fitting some data, at the end of the day, as long as the fundamental assumptions are met, methods work, right? The problem is when the fundamental assumptions don't hold. So the easiest example probably is in terms of non-stationarity characterization. For example, in the atmosphere, we expect probably only one change, which is climate change, right? And that's supposed to continuously happen. It's continuously happening over time. However, as you very well mentioned and highlighted, in terms of hydrology over the surface, maybe we can find, for example, an abrupt change, right? That makes sense in some cases. For example, if you have a river and it's unregulated, and at a certain point in time, now you have a dam, well, probably because of water regulation, in terms of floods, it goes down, right? So yeah, it's more challenging in terms of like incorporating our knowledge because we need to understand more detail the hydrological system. But once you make the adaptations to your methodology to reflect acceptably reality, I would say there is no difference in terms of fitting and predictive performance. At least that's my experience so far. I don't know if I will change it probably in the next few years.
Thank you so much.
Thank you.
Thanks both. I have a hand up from Hasti. Please ask your question live.
Hello, hi there. I'm a PhD student at the University of Waterloo, working in two different domains, like a pavement and as well as the hydrology. So, correct me if I am wrong. I didn't find some kind of applications for the small scales environments, like for the urban hydrological modeling. Like if we the technology is evolving, you get more precise DEM data, but when I look through the land cover classes, we still have like around 13 to 15 classes. So this is not changing. Is there a way to precise more our hydrological models? I name it microhydrology. I don't know if that term is correct. Is there a way to get more precise on the pavement to know the storm management, the water ponting on the pavement, and much more? So in that terms, is how can we apply this hydrological? Will be a local, will be a regional, or will be a provincials? So these data has been out there for the large scales. How can we dive into the small scales environment? Thank you.
Yeah, that's good question. Like there is always trade-offs. Like we can go like finer resolution, but like as we go finer resolution, the computation time, the load of the like computation grows a lot, like exponentially, for example. So like imagine that like if it takes like 2 days to forecast tomorrow's flow, it's unrealistic. Like it doesn't make sense, right? So we have to always we have to like consider the trade-offs, like how much computational resources can be used to forecast something, right? So like as you said, like for urban watersheds, so if we go finer resolution, that could be better. But also like not only the computational like resources, like but also like the current existing data, like how much fine grids we have so far. For example, like you are wondering like finer, like few centimeter scale, like land cover. But if we think about the like meteorological forcing, for example, the finest one is HRDPS, for example, like 2.5 kilometers grid. So like like we like it, because like yeah, for final resolution we should have like every data sets in very finest grid, but like some, even though some data has finer grids, if the others are not, maybe it's very hard to apply them to find finer grid. And like unfortunately, like the application what I presented used semi-distributed, not fully distributed. So there are if we move to fully distributed model, there should be more computational resources should be assigned. So there's always trade-offs. So sometimes no data, no final data, and second, computational resources.
Thank you very much.
Okay. Thank you.
Thank you. And I think we're going to head to some of the questions we've had submitted through the Q&A now. The next question I think is for you, Cuauhtemoc. And have you taken a look at how the estimates from a non-stationary FFA versus estimates from a stationary FFA with a climate allowance applied differ? And do they look different in kind of predictable ways? Or can you talk a little bit about how those two setups look different or similar?
Yeah, totally. And I'll probably share my screen very quickly to show you this part. It's right here. So here is an example of how they differ, right? So in yellow, you will find the estimates at a given timing point, say the most recent estimate, in yellow using the conventional approach, okay? That's yellow in both cases. These are two different sites. In this case, if you do use the non-stationary frequency analysis, you will find out that the estimate is actually a lower magnitude event, whereas in this opposite case, it is a higher magnitude event. So as you can see, if you ignore the non-stationarity, in other words, if you use the conventional frequency analysis, as long as there is non-stationarity, you will be basically either over predicting or under predicting. And I don't have that figure here, but yeah, we run this again in several sites in Canada, and we found that in places where we found evidence for non-stationarity, the under or over prediction could be as large as plus minus 50% of over or under prediction. I will not completely like blindly believe that numerical results. What I will suggest is just to see there is some like warning there, right? So that requires more attention, probably using more other approaches, including like regional frequency analysis and using process-based models and account for climate model projections. But anyway, that's a warning, right? That you will be potentially missing you will be missing the actual design event that is required for your development purposes, right? I hope I addressed the question.
I think so. And if not, I'm sure that the asker will follow up a little bit. Thank you. Mhm.
Thank you.
Next question in the log from Ashraf. In the double stochasticity framework, how far beyond the 100-year flood quantile can be predicted? Say 200. Do we need to use climate model projection each time we want a Q200 prediction?
Yeah, numerically speaking, I think once you have fitted a distribution to a sample, you can predict whatever quantiles you want. So you can even predict like the 1 million year if you want, because numerically that's possible, right? But probably the question is if you have enough data to make such an inference. Like I can just say that in the conventional frequency analysis, say stationary, they often say that you need at least 30 years of data. And if you have 30 years of data, you can be confident that more or less your estimates are like trustworthy, right? But I will say there's no hard rule like for this sample size, this is the largest quantile you can estimate. Again, my recommendation would be just like acknowledge non-stationarity, sorry, uncertainty. So you will see that as you move toward the higher return periods, like 100 years, 200 years, 300 years, you will notice the confidence interval bounds are getting larger and larger, meaning that you have less and less confidence on that estimate. You can get it. It's just that it's too uncertain, right?
Thank you. I see a raised hand in our log. So Xavier, if you'd like to ask your question live.
Yeah, thanks. Can you hear me?
Yes, we can hear you.
Awesome. You already alluded to this a little bit in your presentation, Cuauhtemoc, but how far off do you think are we from having something similar to what they have in the US, like a general guideline that Bulletin 17C, and why don't we have one? What's precluding us from developing something like that? Thanks.
Yeah, thank you for your question, Xavier. And I understand there are several efforts going on to achieve something similar. I'm not sure if the same thing, but something similar to Bulletin 17C. And for example, there was a call for creating a manual of practice. It's a manual for practice for flow frequency analysis. I believe that's the name, or something very similar. And I believe the outputs of those will be available somewhere soon, probably in a couple of months or so. But I will say that Bulletin 17C is not necessarily an ideal, because, for example, in there they say the institutional distribution is the log-Pearson type 3 distribution, right? So you don't really care if your sample seems to follow that distribution. It's just institutional distribution, and you use it. That's it. Probably, or at least that's my opinion. What we need is a standard way of doing things, like common workflows, coherent workflows, and, for example, find ways to identify what the best fit distribution is, rather than saying just use this distribution blindly, because not necessarily will match every place in a country, right? I mean, what happens in California, for example, is not necessarily the same as what happens in the center of the US or maybe in the Northeast. So perhaps what the improved version offered by Canada is even better than the one from the US, and probably is more about coherence in the way we everyone work. And we work in the same way, and we acknowledge we can have flexibility. We have different project needs again, and different contexts, so probably we have different answers, and that's okay, as long as we follow the same procedure.
Thank you.
Thank you.
Thank you. Our next question is from the Q&A. We had someone ask about the tool HiFran Plus, which includes a similar decision support system to select distributions. Can you comment a little bit about how it differs from your tool?
Yes, totally. I believe HiFran Plus is an excellent tool, and there are some others, for example, CFA, Consolidated Frequency Analysis, and there are some more I know. The difference between those tools and the one I mentioned in this presentation is basically accounting for non-stationarity and incorporating recent research advancements. For example, those tools do not allow you to conduct non-stationary frequency analysis. And also, they do not incorporate the method for model determination I described based on the general decomposition of non-stationary stochastic processes. They also do not use the improved version of profile likelihood method for uncertainty quantification. These are just some examples of how both differ. They are excellent tools if the stationarity assumption hold. That will be my answer. If that's the case, they are pretty similar. So you can use the one you like, and that's it. But then if you want to account for non-stationarity, you probably will need to consider some tools, including the one I mentioned.
Thank you.
Next question we have from Hafiz in the Q&A. For stationary data sets, is there any added value in using FFA framework over other conventional tools?
To the best of my knowledge, at least when we published this work, which was last year, our tool was the most comprehensive one. There are some other tools. For example, I will mention one. There is one developed by the University of California at Irvine. The disadvantage was that their exploratory data analysis tool, in order to investigate non-stationarity, was not as comprehensive as ours. For example, if I remember correctly, they didn't consider non-stationarity in higher order moments. They didn't consider climate change point, as we did, and they didn't investigate the type of trends, and they limited to one parameter estimation method, which was Bayesian inference based on Markov chain Monte Carlo, and they use only log-Pearson type 3 distribution, and I believe probably the GB distribution. So our approach considers more methods and more distribution and gives more flexibility.
Thanks, everyone. A reminder, if you'd like to ask your question live, please raise your hand. We have a couple minutes left, so I'll pass it back to Meg. I think we'll be able to squeeze in maybe 2 or 3 more.
Okay. Our next question is on how to couple GCM data with hydrology models. One concern in doing that is that they cannot capture the magnitude of extremes very well. Magnitudes are quite a bit lower no matter how well one calibrates their hydrology model. In the GCMs, the forcings that are needed to drive extreme weather that we need to consider in the future are not present. Are there any recommendations on how that issue can be managed?
Probably Yongho can complement this, but I believe most likely you will need that stage of post-processing, right? So you have the climate model outputs, could be from GCMs or RCMs, and they will still be probably biased, either most likely underestimating, right, extremes. So what you can do is just bias correct those outputs or statistically downscale them, and most likely that will remove the systematic biases, and now it will be a better input for your hydrological model. That's my 2 cents, but John has more experience with that.
Yeah, this is a good question and interesting and good information, but like this question is somewhat beyond our presentation, I think, because like what we applied is to from the past data, which is RDRS, like, and then like try to develop some guideline for floodplain mapping by developing the model agnostic framework. So like for like GCM with hydrologic models does not capture extremes, is somewhat beyond our scope.
Thank you.
Mhm.
Hey, if you are maybe just interested in bias correction of extremes from climate models, you can look at the paper I mentioned in Water Resources Research, and the codes are available. So if you want to use them, they are freely available, so you can download them and use it for your practice if you want. At least try it, right? Let's see how it works.
Sam, I think you're on mute.
Oh, I'm on mute. Thank you to both speakers. From Hasty, is there a way to enhance the precision of land use and land cover data for urban flood modeling within microhydrology, achieving centimeter accuracy?
Well, that's what like Asti already asked and I replied.
Oh, okay. I can move to the next one. Is the proposed methodology applicable to evaluating low flows as well?
Actually, like as I said in my presentation, like this is the result from the first phase, and like we couldn't even like calibrate the model yet, and so this this question and actually the next question can be answered after the second phase or third phase progress. So like I want to say like keep your eyes on our project and look for our like outcomes.
And I think that answer was applicable to the question on methodologies to estimate storms for use in hydrologic models. Was what you were referring to, Jungho?
No. Like question from Ricardo.
Yeah, okay. Great. Then I think we have one last question. And then I think that's enough time well, will there ever be enough time to thank everyone involved in this? But we'll take the minutes. How significant is the impact of AMC on flood modeling, and what are the best approaches for its evaluation?
Can you add some words, Quatermac?
I guess that's more related to your work, but so AMC, I guess, is antecedent moisture content, probably, right? And again, if that is for statistical analysis of floods, is basically related to the flood generating mechanisms. that was not accounted for in the work I just presented, but that's an ongoing work. So I don't know. I don't have the answer at this point.
Yeah, me neither. But from my creation learning, like when I learned hydrology, like when I tested like various AMC conditions, even for very small differences in the initial conditions, the outcome in the end can be very large. So determining as much accurate as possible AMC condition is very important. Not only the AMC, but all the initial conditions are very important when we run the hydrogen models.
Thank you. Incredible 2 hours of telling us some really interesting information and then the follow-up questions. We really appreciate it, Guatemala and Jongho. We are going to wrap up now. I'm gonna do some thank yous, and then we are gonna turn off our videos pretty quickly. But we are going to leave the chat open for a few minutes just to make sure that people can follow up with some of the links that were dropped. We will be posting the videos in both French and English of this presentation online, and I believe we'll have the slides posted as well in both French and English. I think for this presentation, all the slides will be up. And those will be on the CWA website shortly. I'd really like to thank our two speakers. I'd like to thank ECCC, the NHS, and Emmanuel and her team for helping us get this all together. I'd really like to thank my team as well. Sam and Hannah have really been instrumental in putting this series together. I'd like to thank our interpreters today who have valiantly been going at it for 2 hours, and without them, I think it's really valuable to us that we've been able to present this information in both French and English today. And so we really appreciate all of their work. And thank you all for staying with us. We still have 132 people online at 2 hours. So we really appreciate it. And we hope that you will join us again for future events in this series that are coming up. And you can find those on our website at cwra.org. Have a great afternoon, everyone.
Thanks so much.
Thank you so much.
Thanks, everyone. Take care.